Good morning. Today we will study about the shape of the earth. What are the different terminologies used for defining the shape of the earth? That the earth was a flat like substance. Whenever they travel from one place to another, apparently they thought that they are moving over a flat surface. So from that, people thought that the earth was basically a flat celestial body. So this was the map of the earth which was proposed for the flat earth. Now, like Newton and many others, they first make believe that the earth was not a flat or square body. Instead, they depict, they realize that the earth was something like a round or spherical body, or like a elliptical body. But the fast mathematical calculation about the shape of the earth was done, uh, which is done by a mathematician, or in those days these are the astrologers, named as Eratosthenes. He first calculated the spherical size of the earth using the those days simple mathematical calculation, simple geometries. And he mathematically first proposed that earth was not a flat body, not a square body. Instead, it is a sphere. But now the question comes, is the earth a perfect sphere? The answer is no. Earth is not a perfect sphere. If we look very closely about the shape of the earth, we found that it is like a orange, with its middle part something flared, some more bulgy, and its two upper and lower sides they are something like depressed, some flattened. So earth is not a perfectly spherical body. That is why it is called a oblate spheroid, and it gives earth something elliptical in shape. But it's not a sensu stricto ellipse or sensu stricto elliptical shaped. Rather, the more scientific term to call earth shape is the oblate spheroid, in which the two poles or the polar axis is slightly shorter, and it is shorter by about 1 by 300 times from the equatorial axis. Here you can see the values. The equatorial axis is about 6378 kilometer, whereas the polar axis is about 6356 kilometers. So almost the polar axis is about 23 kilometers shorter than the semi-major axis, that is than the equatorial axis. So that brings the earth somewhat more bulgy near the equatorial region and more flattened towards the polar region. Now, the flattening in the polar region, or the oblateness in the polar region, that can be defined by the flattening ratio, or oblateness value, that is defined as f. It is mathematically defined as the difference in the radius of the two, that is the semi-major axis, that is the equatorial axis A, here it is, and the semi-minor axis, that is the polar axis B. That is the difference between the semi-major axis and semi-minor axis divided by the semi-major axis. So this uh, difference in radius of the earth towards equator and towards pole, that defines their difference, and ultimately the ratio that defines the flatness or oblateness of the earth. Now, why the question comes, why this shape, that bulgy shape in the equatorial portion that occurred or that happened to earth? You may very well aware about the centrifugal force on a centrifugal force of a rotating body. Now, the centrifugal effect of the earth's rotation causes an equatorial bulge. The main departure of the earth's surface from a spherical shape that occurs as we move more from the center towards the equatorial region. So our earth axis is aligned from north pole to south pole, and the centrifugal force is act more and more as we move away from the earth axis towards the equatorial region. So the distance between far, so centrifugal force is more effective in the equatorial portions, and that is why the equatorial region that departs from its proper spherical shape and the equatorial portion becomes more bulgy. Now, if the earth was covered by only oceans, then apart from winds and internal ocean currents, the surface of the earth would reflect the forces due to rotation and the gravitational attraction of the earth to the external bodies. So only two forces are there. If there was no wind, no other internal currents, and we consider that the entire earth is covered by the uh, water body, that means entire earth is covered by oceans, then the only force acting over this uh, outer cover, that is over this oceanic body, is the gravitational force and the centrifugal force due to the rotation of the earth. What we observe in other celestial bodies. Now, when on these ocean bodies, the tidal effects are also removed, that means the tidal effects are also discarded, then the shape of the earth is only due to the rotational force, that is the centrifugal force, and the internal attraction of earth, that is the gravitational force. So these two forces define the shape of the earth. If all other surfacial things, tide, the ocean currents, wind motion, all these things are discarded from the scenario. So now what will happen? The shape of the surface of the earth is now governed due to the variation of density, or in other words, due to the variation of the weight. You all know that weight is strongly related with the density of the component, or with the density of the material. So basically, the centrifugal force or the gravitational attraction force, that will vary depending on the different density of the material. And say for simple example, you know that the density of the continental crust is lower than the density of the oceanic crust. You may well aware about the two types of crust of the earth. Crust is the outermost rigid layer, outermost solid layer, solid skin like layer, very thin. It is made up of two types. One is of granitic composition, that is lighter, called it as continental crust. Another is of basaltic composition, that is relatively heavier, that is the oceanic crust. Now, as there is density contrast between the continental crust and the oceanic crust, so these two crusts may suffer different gravitational force and different attraction force. When all other things, that means the wind flow, the ocean currents, all the tidal effects, those are removed. So different portions of the earth, as it is made up of different materials, they will feel different gravitational attraction and different centrifugal effect. So depending on that, the actual shape of the earth varies from place to place, and uh, that will determine the ultimate shape of the earth. Now, as I previously told you that from the center, this is my rotational axis, and from this center, as the distance of this equatorial portion is maximum, if you consider this distance, if you consider this distance, as this distance is maximum, so the centrifugal force will be act much higher in this portion compared to the other portions of the earth. So that is why these portions, the materials of these portions, try to move away from the earth's rotational axis, that is the centrifugal force, and that makes the equatorial portions more bulgy. Now, coming to the different reference systems, uh, reference surfaces, by which different mathematical calculations are done. So we um, came to know about the from the very preliminary concept of the flat earth, then the square earth model, then comes the elliptical earth. That means throughout the earth, if there is no other external forces, the earth is almost spherical, not perfectly sphere, but almost spherical, like an ellipse, like an oblate spheroid. So those that shape of the earth is known as oblate spheroid or ellipsoid, and it is thought if the earth is covered almost the same material, then it looks like a smooth surface of an ellipse or of an oblate sphere, and that surface is known as ellipsoidal surface. Here you can see this green colored surface. That's a smooth surface. That's a imaginary surface that is not exist originally. It's an imaginary surface when earth is thought of a smooth ellipse that is covering all the places of the earth by the same material. So this surface is known as the ellipsoidal surface. Now, the in actual, earth is not composed of same material in all places. There are variations. There are lots of hillocks, lots of ocean basins, lots of mid-oceanic ridges, trenches. So in these areas, these have elevation differences. Here you can see this black line. So these are the continental portion. These are flatlands, then hills, hilltops, then the mean sea level, then goes to the deep ocean. That is the deep oceanic basins. So you can see that the original earth surface is not at all matching with the ellipsoidal surface. Here you can see the green colored portion is the ellipsoidal surface, and this is our original earth surface. It's very undulating, very uneven. Some places it is much higher than the ellipsoidal surface, and some places it is much lower than the ellipsoidal surface. So this is the actual earth surface. Now, due to these different elevations at different places of the earth, so sometimes it become very difficult to do any mathematical calculations, and particularly when it is required to determine any um, height, altitude, or depth with respect to some reference plane. that reference plane is basically not exist. So on what basis we um, make those calculations, and what will be our reference plane? Because here you see that the ellipsoidal surface is not matching with the exact surface features, exact surface elevations of the earth. There are numerous or havoc perturbations with the original. Here you can see this much additional height, here you can see this much additional height, whereas here you can see this much depth, negative height is there. So for mathematical purpose particularly, people's thought or people's define in more scientific way an imaginary surface which is known as geoid, or often it is called as the geoid surface. Now, what is geoid surface? What do you mean by geoid surface? The geoid is basically an equipotential surface. Equipotential means that over the entire extent of the earth, the potential function is constant. Now, what is potential function? Potential function basically describes the combined effects of the gravitational attraction of the earth and the centrifugal force which acts away from the um, earth's rotational axis. So together these two, they will define uh, the potential function of any point over the earth's surface. And it is an, again I am going, it is an imaginary surface in which uh, all the places of the earth have same equipotential function. Okay, that means it is a equipotential surface, same amount of equipotential amount. Okay. Now that brings this red colored line that is known as the geoid surface. That means over this red colored line, in all the points over this red line, the potentiality or potential function is same. The potential function is constant. Now, here the question arises into your mind that the potential surface or the potential function in this red colored line is constant, but it is not a smooth surface. It is, again, it is showing some undulating nature, uneven. Somewhere it is um, uprising, somewhere it is depressed. So why not it is a smooth surface like the ellipsoidal surface? The geoid surface is not a smooth surface. Again, it's undulating because, as I told you, the geoid surface is defined by the centrifugal force and the gravitational attraction. So in all points over this line, the effect of centrifugal force and the gravitational attraction will be same. Now, if you just consider the gravitational attraction, now this gravitational attraction de uh, will depend upon the weight, that is the density of the material. And as density of the earth surface, density of the earth material varies from place to place, a simple example which I previously gave you, that is the difference of density between continental crust and oceanic crust. So as the density of the earth's material varies from place to place, so the gravitational attraction of the surfacial material of the earth is also varies from place to place. And as the gravitational attraction varies from one point to another, that is why the geoid surface also becomes undulating from place to place. This geoid basically reflects the temperature and density variations of the entire earth column over this portion. Okay, so this actually over this year, this total portion, the density and uh, the temperature condition of this total portion is determined uh, the geoid, what will be the geoid surface. The orthometric height that is defined by capital H of a point of the Earth's surface is the distance from the point to the geoid. So here it is the original surface point. The orthometric height is the distance from this point to the geoid surface. Again, I am telling you that the ellipsoidal surface and the geoid surface both are imaginary surfaces that is used for mathematical purposes. There is no uh, natural existence of the ellipsoidal surface or geoid surface. But you can see that geoid surface is more close to the ellipsoidal surface in contrast to the um, original surface feature. So it was uh, thought for simplification that this geoid surface is basically our mean sea level. That is not actually, geoid surface is not equivalent to the mean sea level, but for simplification, for mathematical simplification, the geoid surface is thought the height of the mean sea level. The geoid surface is also irregular, unlike the reference ellipsoidal surface, which I already told you that it is a smooth surface. But the geoid surface is considerably smoother than the Earth's physical surface. The physical Earth has excursion of about 9,000 meter of the height of Mount Everest, and the deepest part of the Earth's surface, that is the Mariana Trench, of about 11,000 meter. Where in contrast to these original elevation difference, the original height or original depth, in geoid surface, the deviation from an ellipsoid ranges about only 85 meter from the Iceland continent and only minus 106 meter in the southern India. So together the elevation difference is approximately about 200 meter. In contrast, if you look at the original surfacial height and depth, there the original difference is about 20,000 meters. Minus 11,000 is the deepest part, and plus 8,800 the highest altitude part. Now here you can see the question obviously came to your mind that uh, why did not the Mount Everest shows the highest geoid value instead of Iceland that shows the highest geoid value? As I already told you, the value of any value of geoid of any point, that depends on what material it is made up of. Although Mount Everest is in actual, its altitude is height is about 8,848 meter, but the Iceland that consists more lighter materials. So that is why in geoid surface, the Iceland have more values than Mount Everest. Okay. Similarly, although Mariana Trench is about 11,000 meter depth, but in southern Indian landmass, that is made up of more denser material. So that in due to the more density material of the southern India landmass, and the gravitational attraction force is much more there. Okay. So that shows more negative values. Okay, so the main thing is, although the original uh, shape of the earth is different from the geoid surface, The geoid value is basically determined the density of the material and the temperature condition of that particular area. Here you can see the mass excess either subsurface having excess density or positive topography deflects the geoid upwards. Here you can see at this portion, if you consider the present day sea floor, here it is the sea floor, and at this portion the sea floor is showing some bulging appearance, some uprising appearance. So simultaneously my geoid surface that will also show some bulging appearance above this point, because this bulging appearance means that there occurs some excess mass corresponding to the adjacent places. So due to this excess amount of mass, the uh, density of this area's rock column, the total density of these areas rock column will be different than the adjacent areas. So that is why, due to the greater amount of mass in these areas, due to greater amount of density over these areas, this area shows higher geoid value. Similarly, the trenches, the subduction zones, the mid-oceanic ridges where there is um, less amount of material are there. Most of the crust is basically in deep in mid-oceanic ridges. Those are spreading out from the common center. So there, over a certain point, the total amount of rock mass is lesser with respect to the adjacent parts. So those areas show depressed or lower values of the geoid. Okay. Now, this difference in elevation between the measured geoid and some reference shape, particularly the reference ellipsoid, the difference between the geoid shape and the reference shape, that may be your ellipsoidal shape, that may be your original shape, this difference is known as the geoid anomalies. So geoid anomalies are expressed as the difference in elevation between the measured geoid and some reference shape. In most used reference shape is the oblate spheroid shape or the ellipsoidal shape. Okay, so what I previously told you, that the difference between the ellipsoidal shape and the geoid shape, that difference is known as the geoid anomaly. So the geoid approximate, as I already told you, the geoid is not exactly same the present day mean sea level, but for simple mathematical purposes, it is taken, and it was also found that geoid basically more or less follow the mean sea level. That is why it is thought for simply mathematical purpose that geoid is considered as the mean sea level height. The gravitational field of the Earth is neither perfect nor uniform. An ellipsoid is typically used as the idealized Earth, but even if the Earth were perfectly spherical, the strength of gravity would not be the same everywhere, because, as we know, the different portions of the Earth, the mountain ranges, the deep sea trenches, the mid-oceanic ridges, they are made up of different material, and depending on the variation of the material, the density of the earth in those points also vary. So if the perfect sphere were covered by water, the water would not be the same height everywhere. Instead, the water level would be higher or lower depending on the particular strength of gravity in that location. So depending on the, suppose all over the earth the crust is the oceanic crust. So as oceanic crust cools down, we know that oceanic crust forms in mid-oceanic ridges, and as oceanic crust cools down, its density also changes. So although it is made up of same kind of oceanic crust, depending on the cooling, depending on older ages, when the oceanic crust becomes more older and successively it becomes more cooler, the density of the oceanic crust also changes. So if we thought that the entire earth crust is made up of oceanic crust and it is only covered by the ocean bodies, then also as the oceanic crust is made up of different density material, the height of the ocean at different places is not same. That will uh, depend on the density of the material. So in some places the height of the ocean is uh, higher, and in some places it is lower. So that is also depending on the temperature and density condition of the oceanic crust. So this is an arbitrary uh, condition. It is thought that, but in what we found, that earth is composed of continental crust and oceanic crust, and even um, in the present day condition, the ocean height in all other places is not same. So that is also depending on the difference of the density condition of the oceanic crust as oceanic crust cools down gradually with age. Now coming to another property defining the different shape of the earth, that is known as hypsometry. So what is hypsometry? Basically hypsometry is composed of two words. One is one Greek word is hupsos, which means height, and another Greek word is metron, which means measure. So if we sum up the two terminologies, that brings that hypsometry is the science in which the height of the earth at different places are measured. So it is the measurement of height of earth at different areas. Okay. Now in hypsometry, what we measure, that is the positive height with respect to the reference surface, and in most cases the reference surface is the mean sea level, that is the geoid surface. So the positive height with respect to mean sea level is known as uh, hypsometry, whereas the negative height with respect to the mean sea level is known as the bathymetry. The measurement of negative height, that is the measurements of depth in the ocean basins, their measurement is known as the bathymetry. Now the hypsometric curve. So hypsometric curve is a simple histogram in which we plot the uh, elevations of different points over a geographical areas. Suppose you are uh, going from your academic institution, from your college to your house. So during your journey, you are going through different points, you are going through different locations. Now, if you take or if you measure the uh, height, or if you measure the depth on those areas with respect to mean sea level during your journey, you will get different elevation values for different points to the for the entire path from your academic institution, from your college to your home. Now if you plot a simple biaxial diagram, simple xy diagram, where in y-axis you put the um, elevation values, that is the height or the depth values in y-axis, and in x-axis you put the location names during your journey path. So this simple binary plot, this simple biaxial diagram uh, in terms of histogram, in terms of bar diagram, simple, that will provide you the hypsometric curve. Now, on Earth, the elevations can take on either positive or negative values. As I already told you, the positive values are for the um, higher altitude parts with respect to mean sea level, and the negative values for the deeper parts in the ocean basins with respect to the mean sea level, that is the below sea level parts. So together they show a bimodal distribution of the height or depth, bimodal distribution of hypsometric curve. In contrast, in other planets or in other celestial bodies, they show a unimodal distribution of hypsometric curve. Now, why this occurs? Here, as I told you, the hypsometric curve is the um, histogram or cumulative distribution function of elevation. What we actually do, suppose you are going from your academic institution, your college to your home. Now, during your journey in this area from this point uh, to this point, okay. So from this point to this point. Now, during your journey, you take the measure of every point in your journey path. You take the measure of the altitude, or you take the measure of the height, or you take the measure of the depth of every point during your journey path, during this entire path. Now, during your journey path, you get lots of places occurs above mean sea level. This is the present day sea level. You get lots of places above mean sea level, and similarly you may get many places which occurs below sea level, such as the large lakes. They may occur below sea level. Okay. Now, suppose you get 100 points or 100 locations altogether during your journey. Now, among these 100 points, there may come many points which give exact same height values or exact same depth values. Suppose uh, this point, and this point. These 2 points give you the exact value. It may occur, or these 2 points, this point and this point, give you the exact depth value. Suppose this will give you if 5 kilometer depth, this is also give you 5 kilometer depth. This value gives you 3 kilometer height, this value gives you 3 kilometer height. So you may have more than one points having the same height or having the same depth values. Now, what we do actually for hypsometric curve, we take the elevations in the y-axis, like this one, elevations in the y-axis, and in the x-axis we take the number of locations or the number of points having that exact value. So here you can see that 0 meter mean sea level, we take uh, these numbers of points, that is 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So 0 meter altitude, 0 meter height, we get for 14 points, 14 locations. Similarly, this value, this will be about 2 kilometer height, that we get in for only 2 points, only 2 locations. Similarly, this one, that is 2 kilometer depth, that we get only for 2 locations. Here, that is about 6 kilometer depth, that we get for 3 locations. So ultimately, what we did, we take the elevation values in y-axis, and in x-axis we take the number of locations uh, over the entire journey path for our small example. For entire earth, that is considered of the for the entire earth surface at different locations, what are the height or what are the depth values. Now if we plot the heights or depths of the entire earth, we can see that there are two peaks. One peak is here and one peak is here. These two peaks described us that these are the most frequently observed or most frequently encountered heights or most frequently encountered depths. That is the known as the mean continental elevation, which is about 940 meter, and the mean oceanic depth, which is about um, 3000 meter approximately. Okay, so these are the mean values, that means most frequently encountered height and depth values over the entire earth surface. So that is why, as these are the most frequently entered height and depth, so that means the number of points, number of locations having that particular height or having that particular depth will be more compared to other heights or other depths. So for elevations, mean continental elevation, that will give a peak value, that will give this peak, and for similarly for depth, mean oceanic depth, that will give you another peak, and that will occur due to the different composition of earth crust. We all know that earth is made up of two different type crust. One is oceanic crust and another is continental crust. Now oceanic crust is made up of basaltic material, we all know, and this basaltic material is much higher in density compared to the continental crust, which is made up of um, granitic in composition, granitic to andesitic in composition. So this granitic andesitic composition continental crust is lighter than the basaltic composition oceanic crust. Due to this different composition of earth crust in different areas, that will give you two different peaks in two different areas. Now, both types of crust are thought to be floating over the mantle. Mantle, as we know, it's a semi-viscous material. Now, the lighter continental crust floating higher than the denser oceanic crust. So that will bring two different uh, peaks of elevations for the continental peaks and for the oceanic depth peaks. So that is why the elevations over the entire earth surface will show a bimodal distributions. In contrast, the other celestial bodies like Venus, Mars or other bodies, as we know that their entire surface, outer surface is made up of single material. There is no different oceanic crust or continental crust. All is made up, all on the surface is made up of single material. So that is why there is no oceanic body or there is no uh, continental part. All the surface is of continental crust, no ocean is there. That is why they show a simple unimodal distribution like this one. So as earth has ocean, it is made up of oceanic crust and the continental crust, and these two crusts have different in density, so earth shows this bimodal distribution. In contrast, other celestial bodies, they have a uniform uh, crust material, that is why they show a single peak hypsometric curve. Now, the mean depth of the ocean basins is about 3.8 kilometer, whereas the mean height at the continents is about 0.8 kilometer. The mean elevation of the land surface above sea level is called the continental freeboard. That is this portion, mean continental elevation, 0.8 kilometer, what I told is known as the continental freeboard. Now, this intersection of the hypsometric curve with the present sea level, this is my hypsometric curve, and it intersects at this point. Okay, this suggests that about 29% of the Earth's surface is above the sea level. So about 71% of the Earth's surface, most of the part of the Earth occurs below the mean sea level. Now, if through time, as we know, through time the sea level is changing. So our sea level is present day mean sea level is not fixed or not constant over the entire 4.6 billion years time. Sea level sometimes become more much higher and sometimes become lower, depending on the periodical cooling and hot time span suffered by the earth. So during cooling period of the earth, sea level drops, whereas during the hotter condition like today, the sea level rise because more and more ice melts, whereas during cooling period much of the water becomes ice, and so mean sea level drops down. So whenever the sea level changes, that means whenever sea level drops, sea levels becomes much lower than the present day, more and more continental part, more and more land part will be exposed. Similarly, whenever sea level increase, more and more land part will be submerged under the water. Okay. Hypsometric tints are the color bands uh, indicating different elevations. Basically, these color bands placed between the contour lines. That means the lines having the same elevation difference or same depth for two different heights. That the portion is defined by same color level. That is why it is also known as color banding or elevation banding, elevation coloring or hypsometric coloring or elevation tilting. uh, so for altitude it is known as hypsometric tints. Similarly, for depth, it is known as bathymetric tints, that is for beyond oceans. Now, there are some definite color schemes. Uh, for bathymetric tinting, that is to convey the depth of ocean, the shades of blue are used. Lighter shades of blue are used for shallower level, and darker shades of blue are used for deeper level. Similarly, for continental landmass, to define the elevations, to define the height over the mean sea level, uh, it is used from yellow to brown to gray, ultimately white. So for yellow and brown, yellow is the lower height, then brown indicates much higher height than the yellow, then gray color indicated much higher height, and ultimately white color, that is the snow peaks of the higher altitudes, uh, that is the highest elevated part. So from yellow to brown to gray to white, that indicates successive increase in height or successive increase in altitude in the land areas. Here you can see that these portions are something brownish uh, or yellowish, then there is brownish. So these are the lower elevated part, lower height part, these are the much higher height part, then gray and ultimately white. So this white portion is the maximum height land part. These are most flat land part, and you can see that this yellowish portion, the flat land part, is maximum in percentages over the earth surface. So that is why this will give you the mean continental height values, that is the continental freeboard, and this will give you a peak for the continental land surface. And these blue colored bodies, these are basically indicating you the water bodies or aquatic condition. These are basically for pond and lakes where there is not much elevation depth difference. But for oceans, you can see that different colored bandings for different elevation difference. The lighter shades of blue, these are for shallow depths, and as we move more to the center part, you will get more darker shades of blue that indicates much and much higher depth in the oceans. Now the last part, a question that if the crust of the earth had uniform density and thickness, what would be the hypsometric curve? That means there is no different continental crust or no different oceanic crust. The entire earth is made up of same type of crustal material. Then, like the other celestial bodies, earth's surface will also show um, a single elevation in hypsometric curve. As the entire earth is made up of same material, so the uh, elevation difference is not uh, much differ from one place to another. Uh, that means the entire crust is made up of almost the same material. If it is so, it is not actual, but if it is so, the entire crust is made up of, suppose it is made up of continental crust, then there is no material difference, there is no much density difference. So as there is no much density difference, earth gravitational attraction force is almost same, and due to that, uh, if gravitational attraction force will be same, then there will be not much elevation or depth difference. So like the other celestial bodies like Venus, like Mars, Earth will also show this kind of single peak hypsometric curve, whereas in present day, as there is oceanic crust and continental crust, two different types of crust, Earth will show this two bimodal distribution of hypsometric curve. This is the present day condition. Whereas if it is composed of same type of crust metal, that will be the result. So thank you. That is a brief introduction or brief description of the art safe, consisting of the fundamental knowledge of the geoid, the hypsometry, the hypsometric curve, hypsometric tints. Go through the uh, study materials, and if you have any questions, contact with me. Thank you.